Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi everyone. Hi, New York people, if you're there. Today we have Praneeth Netrapalli. Praneeth was an undergrad at IIT, and then after that you went to Goldman Sachs for a little while. I guess you had an outlandish lifestyle, and after a turn of events decided to flee Goldman and come to the US, where you did graduate school at Austin, and he's been doing a lot of nice work in machine learning, algorithms, and theory, and recently been doing some work on visual object recognition. Today he's going to talk about a body of work he's been doing on alternating minimization approaches.
Thanks, Shyam. I'll be talking about our work establishing statistical guarantees for alternating minimization. This is joint work with Alek, Anima, Prateek, Sujay, and Rashish. I'll start the talk by motivating our work with an example. The example I'll be using is that of matrix completion. Say this problem arises from, say, movie recommendation systems, where we have a user movie rating matrix where we observe the ratings of some of the movies by some of the users, and we want to use this information to predict the remaining ratings. This matrix has a lot of structure because the ratings of the movies by users can usually be explained by the movie features such as genre of the movie and actors in the movie and so on, and the user preferences for the same. There has been a lot of theory on how to solve this problem using convex relaxation techniques. However, in practice, these are not the algorithms that are used. In practice, what is used is based on this simple observation that if we knew the features of each movie, say we knew the genre, actor, directors, and all those details about each movie, given the movies that a user likes or dislikes, we can predict the preferences of a particular user. So we can do this for all users, and once we know the user preferences, we can go back and estimate the movie's features. So we can guess one, use this to guess the other one, and then do this back and forth. Even though this algorithm is used a lot in practice, and it seems to predict these rating matrix quite well, there have been very few theoretical guarantees regarding its performance. In particular, it was not well known when this algorithm works, and when it does, why it does so. And this sort of situation is common for many machine learning problems. In particular, for many of these machine learning problems, it turns out that there are provable algorithms that solve these problems exactly. However, in practice, we don't use these algorithms, but use efficient heuristics. These heuristics turn out to have very good empirical performance, but we don't know why they do have such good empirical performance. Our work tries to bridge this gap by understanding why such efficient heuristics, which are used in practice, do work so well in practice. The heuristic that our work focuses on is called alternating minimization. Alternating minimization is a meta heuristic for solving a large class of optimization problems. Suppose we want to minimize a function f, where the variables can be partitioned into two sets, u and v. We choose a random u, and we fix this u and optimize over v, and then we fix this v and optimize over u. In many of these machine learning settings, it turns out that even when the global optimization problem is hard to solve, we can solve each of these individual problems very efficiently. And because of this efficiency, empirically, this algorithm is very widely used. For instance, the k-means algorithm for learning mixture of Gaussian random variables is a specialization of this approach. And empirically, it has also been observed to have very good performance. However, on the theoretical side, in most of these settings, the only guarantees that are known regarding its performance are that it converges to a local minimum. Our work establishes theoretical performance guarantees for alternating minimization in three different settings. The first one is matrix completion, which is what I just mentioned. The second one is phase retrieval. This arises in optics, crystallography, and more physics sort of fields, where we can observe magnitudes of linear measurements, but we do not measure the phase information. So we want to recover a complex vector using linear measurements, but we only observe the magnitude, but not the phases of the measurements. And the third setting is the sparse coding problem. I'll explain this problem in detail later. Before I proceed, let me illustrate through this plot the key challenge in analyzing or understanding alternating minimization. The plot here represents the performance of alternating minimization with a random starting point on the phase retrieval problem. The x-axis shows the iterations alternating minimization is run for, and the y-axis shows the objective value of the function that we are trying to minimize. We can see that the performance of alternating minimization can be broadly separated into two stages. In the first stage, the error decreases, but very, very slowly. Whereas in the second stage, the error decreases at quite a good rate. And this sort of behavior is common for alternating minimization across many settings. That we have this flat stage and then the decay stage. It seems plausible that we can say something about what is happening in the second stage, whereas it seems hard for us to be able to say anything about the first stage, because at least the error does not seem to be a good indicator of if something is going well or not. So our approach in obtaining statistical guarantees for this algorithm is to come up with sufficient conditions where this decay starts happening, and once we find sufficient conditions for this point, we start alternating minimization right at that point, and we get a decay right from the beginning. So in most of the cases that that we have worked on, it turns out that the sufficient conditions for decay are essentially local convergence guarantees. If we start close enough to the global optimum, then alternating minimization does seem to decay the objective value at a linear rate. And the second part is coming up with this initialization point from which this is guaranteed. So this turns out to be an approximation algorithm where we obtain a point which is close enough to the true optimum, and then we use alternating minimization to refine this point to converge to the global optimum. The high level approach I mentioned is the same across all the three problems that we have worked on. Coming up with a approximate initialization algorithm and then showing local convergence for alternating minimization. However, the details of how we prove this local convergence as well as the algorithms we need to design for initialization are quite different in each of these three settings. And so today I'll be talking about our work on the sparse coding problem. Okay. So the sparse coding problem, also known as the problem of learning sparsely used dictionaries, is given a matrix Y to decompose it as a product A star times X star, where X star is sparse. In applications, Y is called the example matrix. So each column of Y is an example. A star is called the dictionary matrix. Each column of A star is a dictionary element or a dictionary atom. And X star is called the coefficient matrix. The sparsity of each column of X star means that each example has a succinct representation as the linear combination of very few of these dictionary elements. In particular, the first example here is just a 3 linear combination of these dictionary elements. This decomposition problem has many applications, in particular in image processing such as compression, denoising, and so on. I'll briefly talk about one application which is relevant to machine learning. The application that is relevant to machine learning is classification. In theory, most of the classification algorithms assume that the underlying classifier is a very nice function of the features, say linear classifier or polynomial classifier or something like that. Whereas in practice, the sort of applications we encounter are, say, image processing applications where the input is pixel intensities. And if we try to apply classification algorithms directly on this input, it usually results in very poor performance. And bridging this gap by first learning good features from data and using the classification algorithms on this representation usually gives much better performance. The sparse coding representation is one such approach for learning good representations from data, and so as to be able to use classification algorithms on these representations.
So then, what is the dictionary and the coefficients here in this case?
We have done an experiment in the end. I'll show you some dictionaries, some pictures in the, towards the end. Yeah. Given that this problem has so many applications, there has been a lot of prior work on this problem. On the empirical side, there have been extensive applications, especially in image processing, and people have used this sparse coding representation to obtain improved performance in many of these tasks. People have also proposed several heuristics such as KSVD, online dictionary learning, and so on, and all of these are variants of alternating minimization. However, on the theoretical side, things are not so great. There are no guarantees on the performance on any of these above mentioned heuristics, and the only result in this area is the recent one by Spielman, Wang, and Wright, where they propose a convex relaxation based algorithm which can be solved using linear programming and show that it recovers the dictionary in what is known as the undercomplete setting. I'll explain what undercomplete setting is later on in the talk. However, in the practically more relevant overcomplete setting, there have been no recovery algorithms. Our work presents the first exact recovery algorithm in the overcomplete setting. Part of our results and quite a bit more were obtained independently and simultaneously by Arora, Gay, Moitra. So let us see how alternating minimization tries to solve the sparse coding problem. So recall that we have a matrix Y and we want to factorize it as A times X, where X is sparse. So we write this optimization problem subject to the sparsity constraint on X. This is a non-convex problem, and so to solve this, alternating minimization does the following. We choose an initial dictionary estimate A0, and in each iteration, we fix the dictionary and then estimate the coefficients xt, and in the next step, we fix the coefficients and then estimate the dictionary at. I'll detail each of these steps now. In the coefficient estimation step, we do sparse recovery. So we minimize the reconstruction error, fixing the dictionary and constraining the sparsity of X. This decouples into many sub-problems, one for each column of Y or each example. So first column, second column, third column, and so on. And each of these problems is a compressed sensing problem. Compressed sensing problem meaning we want to solve a system of linear equations subject to sparsity constraint on the solution. And this, there are many standard compressed sensing algorithms to solve this problem. And for concreteness, in this talk, we'll assume that we'll solve this using lasso. So the ith iterate will be updated according to this, where we want to minimize the reconstruction error of the ith example, regularized by the one norm of the solution. And this one norm is to encourage sparsity on the solution. For the dictionary estimation step, we fix the coefficients that we obtained in the previous step and then minimize over the dictionary. And this is just a least squares problem, and we can use any standard least squares algorithm to solve this problem.
But presumably, like for your theory, does it matter what algorithm you use for the estimating the coefficients, or do you just need some?
We need robustness guarantees on the sparse estimation step. Lasso has such guarantees. There are other algorithms which any robust compressed sensing algorithm will work.
Why do you use the one norm instead of the number of non-zero coefficients, for example?
Because we cannot, we do not know how to minimize if we regularize it with the sparsity of the solution. Whereas this is a convex problem and we know how to optimize it. So we make a slight modification to the previous algorithm, which is that we have a sequence of numbers epsilon t that are given to our algorithm, and in the kth iteration, after the coefficient estimation step, we threshold all coefficients that are smaller than epsilon t to 0. We can think of this essentially as our confidence level at iteration t. So at iteration, so as the iterations increase, our confidence gets big, is much better, and so we can trust the small coefficients as well. Whereas in the initial iterations, we cannot trust the small coefficients as much, and so we'll threshold them to 0. When I go over the proof, I'll explain where this exactly matters.
Maybe in experiments or something, does it seem that this?
In experiments, this does not need to be necessary. This does not seem to be necessary.
Does it seem to be help or hurt, or just not make no difference at all?
Does not really make any difference. So we can see that we have completely specified the iterative part of the algorithm, but we still have not specified how we want to choose the initial A0. Before I describe the initialization algorithm, which will be an approximate recovery algorithm, let me motivate our algorithm by the most important assumption in our work, which is that of incoherence. So we assume that the examples have a true decomposition A star times X star. So there is a true dictionary A star, and we assume that the true dictionary A star is incoherent. Dictionary is said to be incoherent if any two dictionary elements, that is any two columns of A star, are almost orthogonal to each other. And this is the same as saying that the inner product between them is very small. I'll explain later what small exactly means, but for now let us just say that it is small. This assumption is a natural one to ensure the well-posedness of this decomposition problem, even when we are given the dictionary matrix A star. Because if two dictionary elements were close to each other, then it may be hard to tell apart if a given example is using one dictionary element or the other. This is also a widely used assumption in a lot of prior work, for instance, in establishing the stability of such sparse decompositions. So let us now see what our initialization algorithm is. We want to find an approximate version of the true dictionary. So suppose say we want to find the second dictionary element. The idea we have is that we want to use a lot of examples which share this particular dictionary element. So in particular, these green ones share the pink dictionary element. We put them in a matrix. Since all of these share the same dictionary element, if they used all the other dictionary elements in a random fashion, and since all the other dictionary elements are almost orthogonal to this one due to the incoherence assumption, the top singular vector of this matrix is a good approximation for this dictionary element. So the problem boils down to finding a lot of examples sharing a single dictionary element.
And do you redefine the dictionary elements to, so you're given examples.
Yeah.
And I can well imagine, let's say that the examples, that these four green ones are dependent on, in some old definition, 2 dictionary elements, then you would want to combine.
You will just get a permutation of the dictionary element.
Of the dictionary element. So you're looking for the A, which is incoherent, and given your examples, will do something like this.
Yeah.
Okay.
Yeah. So our task reduces to finding lots of examples that share a particular dictionary element. We'll do this in 2 steps. The first step is to find a pair of examples that share this single dictionary element, and then we will use this pair to find lots of other examples which share this dictionary element as well. I'll explain how we do this in the next slide. So to do this,
which share it and are random with respect to the
yeah.
other ones, though.
Yeah.
It's not
Yeah.
just
Yeah.
share it,
Yeah.
but
Yeah.
you're sharing it random
Yeah.
with respect.
That will be another assumption on the
Good.
yeah.
Okay.
So to do this, we define a graph known as the correlation, which we call the correlation graph. In this graph, each node corresponds to an example, and we draw an edge between 2 examples if they have high inner product. So we have this graph, and the first observation we make on this graph is that if there is an edge between 2 examples, yi and yj, it means that they share a common dictionary element. This is because if they do not share any dictionary elements, they have very few dictionary elements, and all of them are incoherent with each other, so the inner product will be very small. And so since the inner product is large, they have a common dictionary element. The second observation is that each dictionary element corresponds to a cluster in this graph, which means to say that if you have two examples which share a dictionary element, then with high probability they will have an edge between them. This is because all the other ones will be incoherent with each other. Using these two observations, we want to take an edge and we want to say whether the corresponding examples share exactly one dictionary element or more than one dictionary element. And we do this by looking at the edge density among common neighbors. Suppose we pick this particular edge, we can see that they share two dictionary elements corresponding to S1 and S2, and the edge density among common neighbors is far away from 1. Whereas if we pick a good edge, if we pick this edge which share exactly one dictionary element, then all their common neighbors also share the same dictionary element and hence will have edges among themselves. So the edge density among common neighbors there will be close to 1. So in this way we can distinguish whether an edge has one intersection or more than one intersection. Once we find an edge that has exactly one intersection, we can use all the common neighbors to get lots of examples that share exactly this particular dictionary element. And then we use SVD on this matrix to obtain the approximate version of the corresponding dictionary element. A similar algorithm was developed also by Arora, Gay, Maitra. They also present a different algorithm which does signed average instead of taking the top singular component, and it has better performance guarantees.
What's the algorithm?
So once we get these examples, instead of taking the matrix and then the top singular component, you average these according to the signs contributed by this dictionary element. That will also give you an exact approximate version of this dictionary element. And this has better performance guarantees than ours.
Wait, but to get that graph, you're just looking at an inner product graph with a threshold or something?
Yeah.
So literally that graph is you just have a threshold and you put an edge if the inner product is large.
Yeah.
I see. And then you're, okay, I see.
So then, but you know that's the sign of the inner product, so that's how you get those signs?
So for our case, we don't really need the signs because we are not averaging. So SVD takes care of the sign issue. Whereas if you are averaging, you need to know the sign.
So you do the SVD of the neighborhood graph. You make a covariance matrix by
Yeah.
all the points.
Yeah.
I see.
So for instance, in this case, we take SVD of all the examples that are in this blue cluster, and then take the top singular component. That will give you an approximate version of the dictionary element that corresponds to this cluster. And their algorithm, instead of doing this singular component, they do a signed average, and that also gives you an approximate version of the dictionary element. Okay. So now that we have.
Practice, should any clustering algorithm work?
Yeah. I think it should, any sort of clustering algorithm which can find large enough clusters should work.
But that's if you have the original graph.
No, the correlation graph.
That's just saying, yeah, on the graph you might expect any clustering algorithm.
Yeah.
Getting that graph is a different matter in practice.
So now we have specified our algorithm completely. And before I go on to describe our results, let me quantify the problem with some parameters. D here is the ambient dimension. So each example and each dictionary element is a d-dimensional vector. N is the number of examples. So Y has n columns. R is the size of the dictionary or the number of dictionary elements. So A star has R columns. And S is the sparsity of each example in the dictionary representation. So each column of X star is S sparse. And over complete setting means that the size of the dictionary R is greater than D. So we have more dictionary elements than the ambient dimension. This essentially means that the dictionary elements are linearly dependent. And this is what makes it challenging. that you are obtaining.
And that was the question I was asking, basically, also, because you want to combine them, right?
Right, right.
You have to
Right.
to get the independence on the other ones, and they're linearly dependent. So how do you do it?
Yeah. So this is, and that is why sparsity is essential in this problem, because without sparsity there are multiple representations in the dictionary. Okay.
So is that a feature or bug? Why do we want linear dependence in the dictionary?
This is what seems to work much better in practice. So if you want to do compression or something like that, if you do undercomplete sort of representations, it does not really seem to get very good reconstructions and things like that. Whereas if you do overcomplete things, we get much better performance. So the assumptions for our results are as follows. We have a true dictionary A star and a true quotient matrix X star, and we make the following assumptions on the dictionary and the quotient matrix. On the dictionary matrix, we assume that we have pairwise incoherence, which is what we saw before, and the scaling we assume in particular is that inner product between any two distinct dictionary elements is at most 1 over square root d. So d is the dimension of each of these vectors. So if these two were random, then this is essentially satisfied. And this is the scaling that's predominantly used in all prior work on this problem using incoherence assumptions. The second assumption is on the spectral norm. This assumption is not crucial for our results to hold, in the sense that we allow mu1 to scale and our results capture the scaling, the dependence on mu1. But I'll use a constant scaling of mu1 for illustration, since this is also the scaling suggested by random dictionaries. On the quotient matrix, we assume that each column of the quotient matrix has uniformly randomly chosen sparse support. That is, all dictionary elements are chosen uniformly at random in an example. And every non-zero element is drawn IID from some distribution, and this distribution is supported away from 0. There is a lower bound and also bounded by a constant capital M. So these are the assumptions for our results. Okay. So under these assumptions, our result says that if we initialize the alternating minimization algorithm using the clustering based algorithm I mentioned, and if the sparsity is at most d to the 1 over 9, and we chose the thresholds appropriately, then the sample complexity of this problem, which is the number of examples we need to see to recover the dictionary exactly, scales at most as r square log r. Note that this is an undercomplete setting, and so r is greater than d. And once we have these many samples, we also have exponential convergence to the truth. That is, in each iteration of alternating minimization, the distance between our current estimate and the global optimum decreases by a constant factor, say half. So if we want an accuracy of epsilon, then in log 1 over epsilon iterations, alternating minimization gives you the epsilon close solution.
So what do you have d to the 1/9?
So there are multiple bottlenecks here. So the first one is that if we use the averaging algorithm of Aurora Ge Moitra instead of our initialization algorithm, we get this to be d to the 1 over 6, and that is essentially the bottleneck of the alternating iterative part.
So it's more just when the alternating minimization kicks in.
Yeah.
I see. And then do you have this bottleneck like for matrix completion, like compared to the whatever Donahoe's and those guys, or Candace or whatever?
Yeah.
They have some guarantee for the sparsity level in the matrix, and is it slightly worse for alternating minimization to kick in?
Yeah.
Okay.
Even in matrix completion, our results are suboptimal as compared to the convex relaxation based technique results.
But that's just due to the initialization.
Even for the decay of alternating minimization, we seem to, that's where we seem to lose in matrix completion. For the decay to happen, what we can show is that it needs more sample. What we can show requires more samples, but this our result is still suboptimal even for alternating minimization, I think.
But this is just due to the initialization.
Not necessarily due to the initialization, just in the iterative part. Even if you are arbitrarily close, even then the decay in error seems to have some bottleneck in terms of this. As I mentioned, the proof of this result is in two parts. The first one is that the initialization gives us an approximate solution, and the second part is to show a local convergence guarantee for alternating minimization. In the next slide, I'll briefly present the proof outline for the local convergence part of alternating minimization. So, recall that in alternating minimization, we have two steps. The first step was sparse estimation, so where we solve lasso. We have this equation, and this is the update for x t plus 1, and AT is the current estimate for the dictionary. What we assume here is that AT is close to A star. If we knew the true dictionary A star, then we would be solving this problem instead of AT. And by the correctness of lasso, the solution to this problem will just be the true coefficient x star. Since we know that AT is close to A star, this implies that xt plus 1 is actually close to x star by just the continuity of this problem. After this, if we recall, we do a thresholding step based on our confidence in our current estimate of the coefficients. So the thresholding step ensures that the support of our current iterate xt plus 1 is actually contained in the support of x star. This is because suppose an element of x star was 0, then after the lasso step, since xt plus 1 was close to x star, the corresponding element in xt plus 1 was very small. And after the thresholding step, we would have set it to 0, and so the support of xt plus 1 is contained in the support of x star. This is very important for our results, because if we establish something on the support of x star, which is just one random matrix, then we essentially have the same property for all the iterates in each and every iteration. So we do not need to use a union bound or anything of that sort.
So it could be the case at the beginning you don't have the right support.
Yeah, but by the thresholding operator, we always ensure that our support is a subset of the true support.
It's a subset, so it's actually growing.
Yeah. So in particular, in the beginning iterations, we capture all the large coefficients, and as the iterations progress, we start to capture smaller and smaller coefficients. Okay, so these are the two things that we get after, and note that since we are thresholding only very small elements, we really do not disturb this, because we are only changing the matrix xt plus 1 by very little numbers, because we are thresholding only very small elements to 0. And in step 2, we will be solving this least squares problem, where we update the dictionary AT plus 1 with this argmin. And we actually use these two assumptions to show that AT plus 1 is much closer to A star. And it is very important that we have this sort of a structured error in our estimates. If we did not have something like this, and if we only had xt plus 1 was close to x star, using the robustness of least squares, we could again say AT plus 1 was close to A star, but then it could have the distance could have grown as compared to the distance in the previous iteration. And it is very important for us to show that the error in fact decreases by a constant, at least a constant number in each iteration. And for that, the most crucial observation is that the errors are structured. And in all of our results in alternating minimization, this is essentially the crux of the result. This is to understand the structure of the errors and see that they in fact are not arbitrary and adversarial. Okay. So we tried to implement this algorithm in practice, and it turned out that the initialization algorithm was giving us the same dictionary elements over and over again. So then we realized that there is an issue with our initialization algorithm, which is that if there are dictionary elements which are used with very low coefficients, then they do not turn up in the correlation graph, and so we will not find them.
Is that why it's slow in the beginning, or was that something else?
No, that was something else.
Okay, that's something else.
So we developed a practical variant of this algorithm, including the initialization algorithm, which is as follows. Suppose we want to find 200 dictionary elements, and we use a batch size of 5. We take the examples, and in the first iteration, the residuals is the same as the examples. We do this clustering algorithm on the residuals. We get 5 dictionary elements. Instead of 200, we just get 5. We use these to do the alternating minimization. Then we compute the residuals, and then we do this clustering algorithm on the residual graph, get 5 more dictionary elements, get a big 10 dictionary element matrix, combining this with the previous dictionary elements, and do alternating minimization, and then proceed, keep doing this until we get as many dictionary elements as we wish to get. So we implemented this algorithm on mnist data set, which has 60,000 images of handwritten digits, and here are the original and reconstructed images. In particular, here we took each 8x8 patch and we coded it using just 5 sparse reconstructions. So 8x8 is a 64-dimensional vector, and we use 200 dictionary elements and reconstruct each of these patches using just 5 sparse reconstruction. And these are the reconstructions. And the dictionary elements that we obtain on these things look like this. So we can observe that these dictionary elements are localized and oriented, and in particular they are like lines and blobs and things like that. And this is also one of the reasons why sparse coding representation has received so much attention, because this is apparently how neurons fire in visual cortex of people and so on. Okay. So to summarize, we saw that alternating minimization is a popular empirical approach for solving many problems, and it usually has good performance in most of these settings. And our work establishes the first theoretical guarantees for alternating minimization in various settings. A key component of our results is the initialization schemes, which give approximate recovery algorithms and ensure that alternating minimization, when started from this point, these initialization points, does actually converge provably. There are a lot of directions for future work in this area. The first one is that even though we have results for this algorithm in these different settings, the proofs of all these things are quite different from each other, apart from the high level structure. However, alternating minimization seems to work very well in general for many problems, and it is plausible that there is a general theory behind alternating minimization, and it will be very interesting to see if we can come up with a general understanding of when and why this heuristic works. The second one is motivated again by my first picture, which is that alternating minimization has these 2 phases, which is the flat phase and then the decay phase. And in random initialization, this flat phase seems unavoidable, but it is not at all clear what is happening in this flat phase. Is it that it is just going around and somehow luckily landing in the right place, or is it doing something that's not really captured by the error, is not completely clear. And it will be very interesting to understand which of these cases is true here. And finally, the goal of any of this work or all of this work is essentially to use these intuitions to develop more efficient and robust algorithms for practical problems. And in this direction, we have been working with Shyam on image classification on ImageNet, trying to come up with the right sort of representations which help for classification and many of these other tasks as well. And we hope that our intuitions in these optimization algorithms help us to get a better idea on how to design algorithms for obtaining these representations as well. So this is it. Thank you.
So I have a question. So just something a little counterintuitive. So in your algorithm, you can start the algorithm when things aren't correct, meaning that you don't have the correct support set.
Right.
And it converges to the right answer. But if I understand correctly wrong, your guys' algorithm, you basically nail down the support set right at the beginning.
Yeah, so you want to answer?
But what seems odd about this is it seems like more natural that you would hope the algorithm can work without getting the support set correct at the beginning, but you get a weaker guarantee. Because if you initialize it sort of from that starting point, you get a better guarantee, right, in terms of the
So that is essentially the suboptimality of our initialization algorithm. So in particular, so their averaging sort of algorithm can get you exact dictionary elements if you had infinite samples. Whereas this SVD sort of algorithm.
Right, but somehow it feels nice that in practice that you have an algorithm which sort of doesn't need to have the support set correct right at the beginning. Because this is a pretty strong, and you have that here, but somehow it works with weaker, I mean, you don't get as good a rate. You have this like d to the 1/9 as opposed to 1/6.
Yeah. Well, so if we use their initialization algorithm with alternating minimization, we'll get d to the 1/6.
But then you're starting it sort of with the correct support.
No, it need not be the correct support.
No, even then, it's not the correct support because in our work we have an additional assumption that the entries in this X matrix cannot be very close to 0. So after thresholding, you get the exact support. So, but in their case, it's very possible that it's very close to 0, and then after thresholding.
Oh, I see. Because you don't have a lower bound.
Right.
So we have a lower bound for the initialization algorithm. So since I presented both the results together, we have the lower bound assumption, but we use the lower bound assumption only in the initialization algorithm, not in alternating minimization. So we don't need to get the support set exactly in the first iteration. So the support set could have errors, and then alternating minimization will correct errors as and when it gets to the appropriate levels.
But if it was a lower bound, maybe threshold would.
Yeah. Yeah.
So, if I understand what you said, you can, if I want to run alternate minimization in practice, I can either just run it from a random starting point and tolerate the initial slope being not that great, or I can use your fancier initialization scheme. So in practice, is it worthwhile to use the fancier?
So in one of the things, so we have these three things in phase retrieval. On some of the experiments we ran, it turns out that if we initialize it in a principled manner, the sample complexity is better by a constant factor. This is in experiments again. But apart from that, we have not really been able to come up with a practical reason for using a initialization algorithm, especially given the computational cost of the initialization algorithm. For a random point, you just get a random point and start. Whereas for this, you have to run the initialization algorithm. It will take a lot of time, and then do this. So I would say that we have not seen any real need for this initialization algorithm in practice.
But it makes it something you can analyze.
Yeah, this is something we can say something about, whereas random initialization is still open.
But somehow I think the last experiment was interesting that it sort of didn't work when you ran at the beginning. Like, it's plausible that most of the cases that work in practice are working because those are the easier cases, and these harder over complete cases, like you try it and it just doesn't work. Like the first thing you tried on this digit thing,
So actually on this digit thing again, random initialization does work.
But you have to do it in phases though. The point is like
so this was, we did our initialization at once, and that was giving us only like 5 dictionary elements, 5 distinct dictionary elements.
Okay.
So we had to do our initialization algorithm in phases. Whereas if you choose random 200 patches out of the image that are far apart from each other in a reasonable way, and do alternating minimization, it runs just fine.
I see. Right. Okay. But that's again some sort of time initial. That's like k-means plus plus. So that people do in practice.
Yeah.
A lot.
Yeah.
And that again is very far from the random initialization.
Yeah. So if you initialize these things by random vectors, then it will not work. But if you initialize them randomly from among the patches and ensure that any 2 dictionary elements are not really close to each other, then it just works fine. You have to come up with like very simple heuristics to avoid bad cases in the initialization, and then it seems to work.
K-means plus plus is used all the time for division stuff. you take patches and take things far away from them and start from that.
Okay.
Thanks again.